are finishing up this chapter 1. So a couple of more topics in terms of, so now we see how a silicon as a material behaves. Again, so far in our discussion is it's a pure silicon. Again, it's neither good conductor nor a good insulator. So all this movement of electrons that are going from valence electrons to the conduction electrons, that creating this electron current, hole current is all happening within the structure of silicon. But again, this current only accumulates for either nanoamps or picoamps, extremely small current, not enough to provide any appreciable or decent amount of current within the material itself. But in order to make this intrinsic silicon, again, remember that intrinsic silicon is the silicon, its pure state. But in order to make use of this silicon to a better properties, we need to turn it to either N-type semiconductor or N-type silicon or P-type silicon. So these two are extrinsic type of silicon material which are impure, meaning that some impurities will be added to the pure silicon. Pure silicon is in its perfect state. All you have is that little bit of electron current and hole current, not extremely high to have any decent current. So semiconductors do not conduct electric current very well, and even if they conduct, it's extremely small in their pure state. Again, all that current we've been discussing is all happening at the room temperature only, under the influence of heat. This is because of you have extremely less number of valence electrons, which may later on becomes free. So in order to modify the pure silicon, it must be carefully modified. But how we are trying to modify it? We need to make sure we either increase the number of electrons or negatively charged particles, or we increase the amount of positively charged particles inside, so that we will make something useful out of that intrinsic silicon. So if you make the number of electrons higher, that will become an N-type material. If you make the number of holes higher, that will be P-type material. Because remember that by default, you have equal number of positively charged particles, equal number of negatively charged particles. Protons or neutrons or electrons are equal. But if you make more electrons, then it would become an N-type semiconductor. Not yet. Too soon. So next coming slides will show us what really an N-type material is and how can we make one. Same as for the P-type is, if you have an excess of positively charged compared to the electrons, then it would become a P-type material. The process of doing it is called as doping. So doping is a process that is used by adding what is known as impurities and make impure silicon. So pure silicon to an impure silicon can be done by a process known as doping, which is usually happens at an extremely high temperatures and specialized equipment in order to convert pure silicon into impure silicon by adding. It's basically you take pure silicon, you add some additional material to it carefully, and you either make it N-type or P-type depending upon what material you are adding to that silicon. And those two impurities will lead on to N-type. So when we say N-type material, that material has very rich in electrons. Since electrons are negatively charged particles, that N actually implying that it's extremely high electrons. The number of electrons are very high compared to the number of positively charged. And the term uses is majority charges. In N-type, the majority is electrons, the minority is the holes. But in P-type, the majority is the positively charged, the minority is the negatively charged. It basically shows the amount of, if you have more electrons compared to the positively charged, that's the N-type. If you have more positively charged compared to the electrons, it's a P-type. So more electrons than positively charged, it's N-type material. Because remember that N electrons are negatively charged particles. So remember that you mentioned N is negative, P is positive. That's actually implying electrons and holes. Since electrons are negatively charges, N is for the electrons. Yeah. Yeah. Again, we will talk about each one down the line, but that's what they meant. So if you increase the holes, it will become the P-type. Yeah. The process by adding these called as doping. For example, if you're increasing the electrons or increasing the holes, the process of doing it is called as a doping. So let's start with what this N-type material is. As you see here, it's indicating that the N-type material, the majority carriers are electrons, the minority are holes. So how to make an N-type semiconductor is, remember that we are trying to make more electrons here, correct? So what will be done is, we take silicon, we add what is known as pentavalent impurity atoms or pentavalent atoms. So what are these pentavalent atoms? Penta is for 5. Valent means that's a valence. So when you say pentavalent, that means there are 5 electrons in the valence shell. So if you take that material, if you take that atom, for example, it's showing that Sb as a pentavalent atom. So Sb is for antimony. So that's the material name of it. Of course, you can take phosphorus. That's Phe is a phosphorus is a material. Arsenic too. So any material that has 5 electrons in their valence shell. You can pick any material that has a 5 electrons in the valence shell. Remember that valence shell is the outermost shell. If you take that material and combine with silicon, what you will form is an N-type material. But why pentavalent? Of course, that provides more stability and rigidity to the material. But what will happen if you do that? Because remember, silicon have only 4 electrons in the valence shell, whereas a pentavalent has 5 electrons. That means you have 1 electron is already free, that is readily available. For every pentavalent atom, you got a 1 free electron. So if you have billions of pentavalent atoms, you have billions of free electrons that are readily available. Combination of atoms is a molecules, but individually it's an atom. But if you combine group together, group of atoms is called as a molecules.
So that's 2 different elements. Is that a molecule?
It is a molecule because they are bonded already. Yes, it is referred as, the whole structure is referred as a molecule. So group of molecules is a material. So if you have silicon, all requires is a 4 outermost shell electrons. Previously we showed with the bonding, right? Covalent bonding. 4 with original valence plus 4 with the shared. But now this pentavalent atom has a 5 electrons. So that 5th electron is, with the application of little bit of heat energy, that electron is already become free. So we have already a free electron that is available, and the stability is still there. Correct? It's still being bonded covalently, because remember, covalent bonding is 8 electrons. So the atom, this internal atom, is still bonded covalently with all silicon. Further, you have 1 free electron because you are using the pentavalent. So if you combine with a huge pentavalent impurity atoms, you have all these electrons are readily available for you. That's why pentavalent also referred as donors. So what they are donating? They are donating 1 electron, correct, per atom. That's why they are called as donors. So that's what a N-type material is. It is nothing but you take a pure silicon and you add with pentavalent impurities which are rich in, which has 5 electrons in the valence shell. That will gives us the N-type material. This is usually done in real time. You extremely apply very huge voltage to the material. So the material actually generates a vapor out of it. And you cool them down later on after adding the impurities. So this requires an extremely thousands of volts to even vaporize the silicon altogether. And then you cool it down so the molecules will come back by adding with. So you basically combine 2 vapors together and then cool them down so that they get back to their solid state. So that's the N-type doping. But for P-type, remember, P-type means they are very rich in holes. That's why the majority is holes, minority is the electron. But what materials do I need it? It's a trivalent. So what is tri means? 3. So whatever the material you are choosing, there's supposed to be 3 electrons in the valence shell, such as boron. Boron has 3 electrons in the valence shell. As you can see from this structure, when boron was added to the pure silicon, remember that in order to have a covalent bonding, you need 8 electrons. But you see here, silicon has 4, boron has 3. So you only have 7. That means there is a vacancy available after sharing. So this vacancy creates 1 hole, but if you have billions of atoms, you're going to have excess of holes compared to the electrons. That's why trivalents are not donors, but there are acceptors, because you have a vacancy right there. Once you have a vacancy, that's a hole, correct? It can be filled by an electron, correct? That's what holes are, right? Yes.
So that means both of these, it's 4 parts silicon, 1 part on each one?
On each one, pretty much, yes. That is correct.
So if you have like 4 grams to 1 gram.
That is true. Yep.
4 grams.
Because the more material you dope with, then you're gonna increase the concentration. but those are actually controlled carefully. So there is a way using doping with the extensive equipment, you can by number add certain amount of molecules. You can carefully add, okay, I need 10,000 or 20,000, 30,000 atoms or molecules. So it is possible to do that. And usually such equipment will easily be the size of this room, that one equipment that does doping. Because the amount of voltage, as I said, this material has to be converted into a vapor. So if you think about a silicon crystal, for example, under what temperature it turns into a vapor. So you're looking for like 30, 40,000 kilovolts. It's an extremely huge voltage, and that equipment is extremely, of course, costly as well. So usually these done, there are some fabrication industries. There is actually one in Norfolk State University. There is a one big room that's actually equipped with a machine that converts that. And I think there is one in the ODU as well.
So they fabricate their own chips?
The research. So, and it is possible to fabricate own chip by doping. But mostly the big companies like Intel, all those, they will actually get these materials from outside for their design. So like P-type wafers, they're actually called as a wafers. That looks like a circular cross section with like a notch right there, like a flat notch. So based upon where that notch is, we can tell whether it's an N-type or a P-type material. There is usually an indication on these wafers. So that's a P-type, is you need to dope with a trivalent where you have an excess of positively charged. N-type, you need to dope with pentavalent where you have 5 valence electron. So basically you have an excess of electrons in there. So as opposed to a neutral atom where you have both equal positive or negatively charged. So that's the P-type and N-type semiconductors. Again, if I have a P-type and N-type semiconductor, again, there is no such device based upon purely P-type semiconductor or purely N-type semiconductor, but useful devices can be formed by putting them together. This is the base for every analog electronic device that we deal with nowadays. Since the invention of p-n junction,